All right, guys, this is a quick tutorial on one of the next phases of Unit 7. So as a quick review, we want to just go over enthalpy, and that's what these diagrams are. We've gone over these in class, right? One of these is endothermic, one of these is exothermic. So if you can figure out which is which, this is going to be endothermic, and this is going to be exothermic, which means delta H is positive here, delta H negative here. Or enthalpy, right? Enthalpy is H, okay? One of these is way more likely to happen, and it's this one, okay? Because obviously the activation energy, if you look here, right, activation energy is way less than this one. Also, products are at lower energy down here than the reactants, right? Things are going to only react if they put themselves in a better situation, a more stable situation, okay? So you'd think that only exothermic things happen in life, right? So we use this word spontaneous or spontaneity. Oops, if I could spell, that'd be good. Okay, and you've probably heard this word before in a variety of ways, but in terms of reactions, it's a little bit different. Sometimes when you think spontaneous, you think fast. That's not necessarily true. Spontaneous reactions happen with no added energy needed. Okay, so these are like in nature, you know. So for example, rusting, right? Phase changes, things like that, okay? Decompositions, fossilization, right? So it doesn't always have to be fast, right? You think rusting is super slow. So spontaneous just means it happens, just like readily happens in nature, okay? So usually exothermic reactions are spontaneous, okay? And if we had to guess, we'd probably say that. But let me give you the example of the ice cube, okay? Ice cube at room temp, which is like 25 degrees Celsius. So will the ice cube melt at room temperature, right? Think about it. Picture an ice cube out on the table in front of you, right? It's going to melt. So if we were to write out that equation, it would be H2O solid to H2O liquid. Does that require energy to do, or does that release energy? Okay. So think about it, right? You need to add energy because you need to warm up the ice cube in order to do it. So delta H for this is actually positive. I have to put heat in. You could also write this as heat or energy is an actual like reactant. Okay, like I'm adding it in. You can put heat as a product as well if you want to, but that would mean exothermic, right? Heat is released because we can't subtract in a chemical equation. We can only add. So if we want to subtract heat, we just add it as a product, okay? So if we go by our earlier example that only exothermic reactions are spontaneous, how the heck does the ice cube melt? Spontaneously, because it does, right? You put the ice cube out, it will melt with no extra effort from you. Just the temperature in the room alone will melt the ice cube. So in other words, something else must be contributing to this ice cube melting. Something has to overcome the fact that this is endothermic and outweigh that, okay, or offset it somehow. And so what we found is there's this thing called entropy, and that's really what we want to talk about today. Okay, so we'll emphasize that. Entropy is really just disorder or randomness. Okay? So atoms like to be random, right? Think gas particles in a container. They move randomly. They like to be random. They like to be mixed. They like to be in pieces. Okay, they don't like to be confined or solidified and things like that. Okay? So what we find is that the universe sort of tends toward disorder, right? Everything in the universe wants to be more disordered, okay? Because it takes effort to order things. The classic example of entropy is always like the messy bedroom, right? So, you know, you can use this example if you want to, right? To your parents to explain your messy room. But why would you say make your bed when you're just going to get it messy the next day, right? It doesn't seem to make sense. It takes effort to make the bed or clean the room. And it's just going to get messy again because that's what happens in life. It spontaneously just gets messy because it's easier to do that. Okay. And so reactions are the same way. They want to be kind of strewn about everywhere. They're always going to get messy if they can, because it takes a lot of effort to keep them ordered. Okay. So what we find is that entropy wants to be positive, right? It wants to be a positive increase there. Okay. And this is actually the second law of thermodynamics. Remember the first law? So actually we'll start with that just as a review. First law of thermo is energy is conserved, right? Second law of thermo says that for spontaneous processes, always increase in entropy. Okay? Spontaneous processes always increase in entropy overall, like in total, of the universe, we'll say. So not necessarily just the system or just the surroundings, but when you combine that, everything, the delta S, the S value, entropy is S, I should tell you that. The variable for entropy or change in entropy is S. Okay, because we can't use E, obviously, because that's energy. Okay, so possibility would be if delta S is positive, that means entropy increased. And if delta S is negative, it means entropy decreased. So how do you tell? Okay. Well, there's two little tricks that you can look for. And what we find is the first is state of matter. State of matter is impacted by entropy. So if we go solid to liquid to gas, okay, do you think which one is more random, right? Clearly it's the gas, right? So what we see is delta S increases this way. Okay? So if I melted an ice cube, my delta S is going to increase. And we'll come back to that in a quick second. Okay, so that's the first thing is states of matter, right? So we'll just put a little dot right there. Okay, the second thing that can play a role is breaking into pieces. Okay, so more pieces equals more entropy or randomness. Okay, so more pieces, delta S also would increase. So let's take, for an example, salt dissolving in water. You take solid NaCl and you dissolve it in water. What does it turn into? It turns into Na plus and Cl minus, which are both aqueous. Do you think that dissolving salt would give us a positive S or a negative S, and why? All right, so think about that for a second. The answer for this is, we don't know the number, we could look that up if we needed to, is that delta S for this is going to be positive for two reasons. One, I'm going from a solid to things that are aqueous, so that's going to be helpful. It's not solid to liquid, but it's solid to aqueous, which is definitely better, more spread out. The other thing is that I'm going from one piece to two pieces, okay? So this is definitely going to be an increase in entropy. And if you also note, dissolving of salt is usually spontaneous, okay? And that's because the entropy is typically increasing, okay? So let's come all the way back to our ice cube example here for a second. Why does the ice cube melt when it is endothermic, right? So endothermic says it probably shouldn't be spontaneous. What must be happening? Well, solid to liquid. I'm getting more disordered, I'm getting more random, I'm getting more spread out. Delta S is also positive, okay? So the reason the ice cube melts is because even though it's endothermic, it is very positive in terms of delta S. So the fact that the entropy is increasing is outweighing the amount of energy it's taking, or the amount of heat it's taking to get this thing to actually melt. Okay, So what we find is when we're talking about spontaneity, you actually have to talk about both variables. You can't just rely on the enthalpy. You have to rely on the entropy as well. And there's an equation that we've come up with to relate these things. Okay? So the last thing that we want to address is this thing called Gibbs free energy, okay, which is delta G for Gibbs. Okay, that's the scientist that worked on this quite a bit. So Gibbs free energy is basically the energy available to do work. Okay, energy available to do work. So how does that work? Well, we need to figure out if a system is going to be spontaneous or not. So this is where delta G comes in. If something's spontaneous, it means that it is producing energy to do this work, right? So what we find is delta G, when it's negative, means that a process is spontaneous. If delta G is positive, it is a non-spontaneous process under those conditions. Okay? And I'll show you why. I know it might be a little confusing right now, but let's try to figure out why. Here is the relationship, the equation for delta G. Okay? Now, these should be variables that we understand. So here we have our enthalpy, right? Our heat. Here we have our entropy, our disorder. Here we have temperature. This has to be in Kelvin because we don't want to screw up the sign. Remember, in thermodynamics, sign is hugely important, so I can't have a negative temperature, which is why we want to be in Kelvin here. Okay, so if you want to know if a process is spontaneous, you can look at the overall G value because that's factoring in both H and S already. Note that the temperature is only impacting the entropy value, okay? And that goes back to what entropy is. Think about it. Phase changes, things like that. Is temperature important for a phase change? In other words, go back to the ice cube. Does the ice cube always melt? And the answer is no, because if the temperature is cold enough, right? If you walked outside, in the middle of the night and it's 20 degrees outside, the ice cube's not going to melt, okay? So temperature is dependent on entropy. Enthalpy is not temperature dependent for that. So that's why the temperature's over here. All right, so let's see if we can figure this out. So let's make a little chart here. And then we'll call it a day. So there's going to be 4 different possibilities here of sign combinations. I want you to tell me which sign is the most favorable for a process for H, right? In other words, if I wanted to get a reaction to happen, do I want to be a positive H or a negative H, right? Go back to your graphs here. Which one of these would create a situation where my reaction's most likely to happen? And hopefully you said this one, negative. Exothermic, negative H, is best case scenario for spontaneity. That doesn't mean it's definitely going to happen. It just means, it's gonna try, okay? So best case scenario for S. In other words, what's going to make something most likely to happen? It's when entropy increases. So I'm going to put a positive sign there, okay? Now, I'm just going to rewrite this equation real quick right over here so we can play around with it. Look at the math, the way this works out. If H is negative and S is positive, what's going to happen mathematically to the overall sign of G? If this is always minus, right, then that's what's going to end up happening, okay? So what this is going to do is this is going to create an overall negative of G. There's no way that G could be positive here, okay? There's absolutely no way that G could be positive here. And if G is negative, we know that that means it's a spontaneous process. I'll just write yes for spontaneous. Always, always, always. If you have a process that is exothermic and positive delta S, it must be spontaneous. Always, under any temperature circumstance whatsoever. Think about it. Even if temperature was like 1 degree, right? Or even if it was 0, that would just mean this would wipe out and we'd rely on the H. Okay, so there's no scenario where this is actually going to be non-spontaneous. Okay, let's think about the opposite. When would you have a situation where something is absolutely, under every circumstance, never spontaneous? Well, endothermic, losing entropy. Because, come back over to our math, if H is positive and S is negative, this negative sign here, right, the subtraction, is going to flip this sign. And so no matter what temperature we have, because temperature won't be negative if it's Kelvin, we're going to end up with a positive delta G over here, which means no, under any circumstance, never. Okay? So when do we get messy? Right? We get messy when both H and S are the same sign, right? So if this is positive and this is positive, right? If we have positive and positive, then it matters, right? Because I need to know which one is going to outweigh the other. Because if this one's really big, then it's going to outweigh this and G is going to be negative. But if this one's really big, then it's going to outweigh the other one and G will be positive. So we don't know the sign of G. It could be positive or negative. Do we know if it's spontaneous? The answer is we don't know, but we can make predictions. Because what's going to happen now if I have positive, positive, or in this case, negative, negative, right? That's still going to give us the same situation where we have a question mark here. What happens then is that these two become temperature dependent. Okay? In other words, think about the positive, positive situation, right? We have positive, positive. If temperature is really, really, really big, that's going to make this really, really, really big. In other words, the entropy will become more important. Entropy is good, so if temperature is really, really high here, then this is going to work. So this would be spontaneous at higher temperatures. Right? Think back to the example, right? Which one of these is the ice cube example? It's this one. Ice cube is endothermic. Oops. Endothermic. But increases in entropy. So what's going to determine whether the ice cube melts? Well, the temperature, right? Ice cubes melt better and more spontaneously the hotter they get. They will melt less spontaneously the colder they get, right? So hopefully that makes sense. So now we come to the final example. If I'm exothermic, which is good, I'm negative S, which is bad, when will this be spontaneous? It'll be spontaneous when we make this negative more important, and we make this negative less important. So how do I make S less important? I lower the temperature so that this value will then become lower and less and less and less significant mathematically, and it'll get wiped out. Spontaneous at low temperatures. So what's the opposite of melting the ice cube? Freezing the ice cube. Freezing the ice cube is negative, negative. So when does freezing an ice cube work? At low temperatures, okay? So this is just a general guideline for you, but if you can play around with this equation, okay, then you're going to be able to figure out whether or not a reaction is spontaneous or not. And it's based on just simply the sign of the G, okay? So H, we already know a bunch of ways to calculate H. Here's one more, I guess. Temperature, we can get delta S. We can always look up. We'll learn how to do that a little bit later on in the unit, okay? But this just gives you a sense of when will a reaction be spontaneous. It's not just the heat change. It's the heat change plus the entropy change. Those two factors together will determine if something is spontaneous or not. And that is why things happen or don't, right? So last thing I'll say is, what if delta G is approximately 0? What does that mean? Well, it means it's not really spontaneous one way or the other, and it could sort of go either way. So what I will say is delta G equals approximately 0 in most biochemical reactions. Right? Because we want those reversible. In other words, sometimes I want to break down molecules for energy, but sometimes I have enough energy and I want to build molecules using energy. So I want to be able to go back and forth. And if I have really drastic conditions, then reactions aren't really going to be spontaneous very, very often. And so while reactions out in nature tend to be, very spontaneous or not spontaneous, right? Very big delta G or very small delta G. Ones that are in your body that have to go both ways, that we want to be reversible, the delta G is going to be really, really close to 0. So if you actually look up the delta G value of a lot of the reactions in your body, the enzyme reactions and stuff like that, you're going to find that they're only like a couple kilojoules one way or the other. And that's because we want to be able to control that. Okay? So we're going to talk more about this in class on Monday or Tuesday, depending on what block you're in. But hopefully that gives you a sense of spontaneity. Okay? Have a great weekend.